Okay, in this video we're going to continue on looking at some plane figures. I want to specify the term polygon. A polygon, specifically, it's a closed figure formed by intersecting lines and is named by the number of sides the figure has. So a regular polygon means that all sides are equal and all angles also are equal. Okay, with a polygon, we're going to name the different sides, different types here, and I think this is pretty much a piece of cake. Three-sided polygon is going to be a triangle. Four-sided is going to be a quadrilateral. Some of you may automatically write square or rectangle, but basically square and rectangle has specific features. We're going to, just a four-sided figure in general, if that's all we know, the most we can say is for sure it's a quadrilateral. Five sides is a pentagon. Six sides is a hexagon. And eight sides is an octagon. Okay, depending upon what you're going into, but you might do some of these different types of slicing and dicing these figures. I know if you're going into construction or any kind of welding, you probably are going to be configuring, and you need to be aware of something called the line of symmetry. So we're going to talk about each of these figures, and then we're going to focus on line of symmetry and what that means. But I'm just going to write symmetry in here for right now. Okay, so for this first one, we have a rectangle. This is a four-sided figure. The opposite sides are going to be equal to each other. That's what makes this a rectangle. It sure looks like the four corners are at right angles to each other. This one is a triangle. This one specifically looks like it's an isosceles triangle. We're going to cover this again later because it looks like it has two sides are equal. It doesn't look like that third side is equal. This is not a polygon at all. That would be an oval. This looks like it's a square. It looks like all four sides are equal. Looks like the angles are at right angles to each other. So we're going to call that a square. This is a five-sided figure. That's going to be a pentagon. And I was trying to make this look like it is a hexagon, a regular hexagon. And I am not going to put us through drawing an octagon because I slaughter them. I'm sorry. I want to go back now and talk about the line of symmetry on each of these figures, just to be aware of that. It divides the figure into two parts that are mirror images of each other. So when we look at this first one, we can see that, yeah, we can draw a line of symmetry. I'm terrible at drawing a straight line too. I can draw the straight line of symmetry down here and one right here. And it looks like it would flip back and land on itself, or flip over and land on itself. So this one has two lines of symmetry. This one here looks like it would go from the vertex to the midpoint of the opposite sides. It looks like it only has one line of symmetry. Oval, we're not going to talk about that one. A square is going to have a line of symmetry going straight up and down. In other words, intersecting the midpoints of the opposite sides. It's also going to have a line of symmetry from opposite angles. Okay. Pentagon, we're not going to be able to draw one, from opposite side to opposite side because we have an odd number of sides. But I could draw a line of symmetry from one side, from one angle to the opposite side. And so there's going to be 5 of those that I can draw. One from each side to the vertex that it's opposite. So we're kind of seeing a starburst thing. We should be able to draw 6 on a hexagon, intersecting midpoints of opposite sides, as well as opposite angles. I'm not doing too bad on this here. Watch, I say that and I'm going to... Okay. So that introduces the whole concept of line of symmetry. Okay, we can categorize triangles according to their sides and their angle relationships. Equilateral, it has 3 equal sides and angles. So I'm going to use that abbreviation for angles. Isosceles has 2 equal sides and angles. So we saw this one up here as an isosceles triangle. I think you can see that these two sides look like they're equal to each other. These base angles are going to be equal to each other as well. And that's very different from an equilateral where all 3 are equal to each other. And then scalene, there's no relationships. between sides or angles. Okay, so if we were looking at triangles and evaluating according to angles, a right triangle has one angle equal to 90 degrees. Acute all angles, I'm going to abbreviate angles again, are less than 90 degrees. So this is my less than sign. I guess I should be clear about that. Less than 90 degrees. And obtuse is one angle is greater than 90 degrees. Okay. So this next theorem, I'm just kind of flying through a bunch of stuff here. The sum of the shorter sides of a triangle must always be greater than the longest side. You're like, I don't know, some of you may have not heard that before, but that really sets the basis for Pythagorean theorem. I'm going to pull out some measures here. So I wanted to look at this and say, can we create a triangle from those three pieces? These are our two shorter sides. According to that theorem, my two shorter sides need to be longer than the third side. And that makes sense. And yes, we can draw a triangle there. Okay, in fact, that looks kind of like a right triangle. Okay, now I want to take away that smaller one, and we're going to look at these three pieces and see if we can draw a triangle there. Looks like the sum of these two smaller ones is not quite as long as that longer one. And let's see if we can draw a triangle here. So when I start to line them up on the edges, what happens is as I move these around, we can see that I can't get those two shorter pieces to meet to create that third angle that I need to create a triangle. So that's really where our theorem comes from, that you need to have your two smaller pieces, the two smaller sides need to sum to be greater than that third longest side. So that's kind of the basis for Pythagorean theorem, but we're going to identify which sets could be a triangle. So I've got 6, 7, and 12. Okay, the 6 and the 7 are my two shorter sides. If I add them together, yep, I get 13. Yes, we can create a triangle from those three sides. 3, 7, and 15. When I look at my two shorter sides, no, they are not longer. So this would not form any kind of a triangle. Here I have 3, 7. That adds to give us 10. That's not long enough. Over here, my two shorter sides are here. 3 and 8 add to give us 11, and they're greater. That sum is greater than my longest side. So yes, we can get a triangle here. Okay, so moving on to looking at Pythagorean theorem. Pythagorean theorem only applies to right triangles, those with a 90-degree angle. Okay, the sides that create the right angle are called the legs. And the side opposite that right angle is called the hypotenuse. Now the hypotenuse is always going to be that longest side. Okay, some of you may have heard or you remember or recall Pythagorean theorem as a squared plus b squared is equal to c squared. Most of us recognize that. We've had that at some point in the past. But I would kind of prefer you think about it as leg squared plus leg squared is equal to hypotenuse squared, because you have to set it up in that order. So you have to recognize the legs are the 2 feet, the two edges that make that right angle, and they need to be squared and summed equal to the square of the hypotenuse. It always has to be set up in that order. So when I'm looking at this one, I'm going to take these measures and plug it into that equation. So I'd have 4 squared, because 4 is a leg, 11 is the other leg, so I'll have 11 squared would be equal to my hypotenuse squared. My hypotenuse squared is what I'm solving for. I'm going to call that my x squared. So I'm going to go ahead, I plugged everything in. Now I need to square. 4 squared is 16, 11 squared is 121, is equal to x squared. So now I'm working my equation going down. I can't do anything with this squaring over here, but on the left side I can add those together. So I end up with 137 is equal to x squared. And I, for some reason, didn't draw an equal sign. Okay, I'm going to rewrite that again because we're going to mess with this a little bit. Thing is I don't want to know what x squared is. I want to know what x is. So I have to figure out how can I get rid of that square. And so just like adding and subtracting undo each other, multiplying and dividing undo each other. Squaring and square rooting undo each other. And we talked about this a little bit when we were doing order of operations, that squaring and square rooting are inverse operations of each other. So if I want to get rid of a square, I square root. They cancel each other out. But whatever I do to one side of the equation, I have to go to the other side of the equation and do the same thing. So if I square rooted the right side, I have to come over here and square root the left side. So if I plug that in my calculator, I would end up with x is equal to 11.7. Okay, and so that makes sense. That third side is my longest side. It's my hypotenuse. It has to be bigger than the sum of these two. Okay, so on this one, things are a little bit different on this one. I have to figure out x is one of my legs. So how does that impact things? So I'm going to plug in x squared plus 5 squared is equal to 13 squared. So I have x squared plus 25. When I square everything here, this is what I end up with. And so my deal is, with algebra, you're trying to isolate your variable. So I'm going to subtract 25 from each side to get that x squared by itself. So on the left side, I am ending up with just x squared is equal to 144. That works for us. The other thing is again, I need to square root. I want to get that by itself. I'm just rewriting it so that when you look back over this, you kind of don't feel like we did too much too fast. So I want to get rid of this x squared. I square root. So whatever I do to one side, I have to do to the other side. So the square and the square root go away. That eliminates. So I have x is equal to, now I'm asking myself what number times itself is equal to 144, or I can just plug it into the calculator, but this turns out to be a whole number, 12. And so when I say x is equal to 12, that makes sense here, because 12 is less than 13. 13 needs to remain my longest side. I was looking for a leg. My leg is going to have to be shorter. Okay, now I did both of these problems from a very algebraic standpoint. I want to show you, well, actually before I do that, I want to analyze this a little bit. This is weird. I mean, how come, there's two things, ways that these differ. But when I look at this, I plugged everything in over here, I squared everything, added, and then square rooted. So I see a pattern, squaring, adding, square rooting. Over here, when I plugged everything in, I square, subtract, and then I square rooted. How come this was different? I was doing Pythagorean theorem. How come I added over here and I subtracted over here? And it kind of makes sense. I'm solving for a different component. Over here, I'm solving for a leg. Over here, I was solving for my hypotenuse, my longest side. So over here, where I'm solving for the longest side, it makes sense that I'm going to be plugging in, I'm going to be adding before I square root. Here, because I'm solving for a different component, it kind of makes sense. I'm solving for the smaller leg. I'm going to be subtracting before I square root. So that's one thing that you'd want to get, straight in your head before you continue on. Something else that I want to point out, as long as you recognize that you are squaring, either adding or subtracting before you square root, you might want to change gears, and you wouldn't have to necessarily do this using algebra. I've seen students that are very process oriented, and they totally get this, and I'm totally fine with it. They look at it and they see, wow, I have my two legs. So I can go ahead and say, well, I know I'm going to first, right out of the gate, I'm going to be squaring. 4 squared is 16. 11 squared is 121. So they add those things together, they get the 137, and they know they're going to have to square root for that remaining third side. That's totally fine with me, because they're telling me and showing me that they understand these are the legs. I'm going to be squaring, adding, and then square rooting. Whereas over here, if you want to go a little more process oriented, you would look at it and say, okay, I know I have my longest side. I have to start there. I'm looking for one of my shorter legs. So I'm going to take my longest side. I have to start with 13 squared, which is 169, and they just write the square down immediately, and they're going to subtract the square of the leg that they do have. Well, 5 squared is 25, and they get 144, and then square root. And so they're communicating that they understand that they're going to square, subtract, and square root. Okay, moving right along. We're going to go ahead and talk about using the formulas for area and perimeter. The height of the the height of a triangle is very often called the altitude. I'm not sure that you really have to know that, but you might come across that in different texts and so forth. It is measured from the highest part of the polygon and is perpendicular to the base. So if you have a triangle like this, it's going to be at right angles to the base. This is your base. This is your altitude. And you could draw an altitude from each vertex to the opposite side of every angle, but we're not going to mess with any of that. We're going to be focusing on finding the perimeter. The perimeter is the distance around, and it is found by adding up all the sides. Okay, for finding the area of a triangle, you're going to use one of these two formulas. Area is equal to the sum of the product of base times height divided by 2, or 1/2 base times height. Either way, you got to remember, the base and the height are always at perpendicular. They're at right angles to each other. I think probably most students are going to find that the formula area is equal to 0.5 height times base. That's going to be the formula they're going to want to plug in and use, because you're dealing with a decimal and you don't have to worry so much about dealing with a fraction.